In Module 3, we're now going to study a little more deeply the log-normal distribution of stock prices. And in the next section, in the next module or two, we're going to develop some additional insights on the Black-Scholes formula. First of all, we'll just review our earlier development of the log-normal distribution of stock prices. So we're assuming that the ST is a log-normal distribution, which basically means that the returns are normal. These are identical statements that normal returns, independent normal returns, gives rise to log-normal stock prices. Log-normal stock prices are driven by independent normal returns. One of the properties that we know about continuously compounded returns is that if I have any period from, say, T0 to T2, I can split that period into two non-overlapping periods, and the continuous return over the full period is just the sum of the intervening, the sub-period returns. Now notice that this formula is not true for annualized returns. Okay, this is just the numerical value of the continuous return from time 0 to 2, T0 to T2, is equal to the numerical value of the first period return plus the numerical value of the second period return. If I annualized each of the returns, then the formula will be more complicated. So here we're just looking at the numerical value of returns for the period, not the annualized version of those returns. If we want to use annualized versions of the return, then the return for a period, for example this one, would be the annualized value times T2 minus T0, if everything is expressed in years. Right? So this is a formula in the numerical value of the period return, not the annualized values. This generalizes that if I have a period, say 0 to T, and I break it up into n equal subintervals, which we've been doing right along, for example, in our binomial lattice model, then in fact, the numerical value of the continuous return over the full period is the sum of the numerical values of the sub-period returns. Once again, if the returns are IID, independent, identically distributed, and they have a mean and a variance, then what we find is that the mean and the variance of the full period return is proportional to time. That's what these formulas tell us. And this goes back to a comment I emphasized where I was emphasizing a point earlier. Namely that when we're looking at returns, it's the mean and the variance that we assume are proportional to the interval of time, not the mean and the standard deviation. And you see why that's true. It's true because in this simple summation, the mean and the variance of R, because they're independent, is nothing more than the sum of the means and the variances of the subinterval R's. And therefore, we get a factor of n in both the mean and the variance. And that's what gives us the time proportionality. So a typical log-normal model of stock prices is to define a unit of time, a unit of one, to be a year. You do not have to parameterize your model that way, but it's a common way that one finds in the financial literature. It's just simpler, is to calibrate your model so that the parameters you see are annual parameters, and then you must insert an appropriate delta t in order to convert it to the period return. So we're going to assume that our basic parameters for a full period, a period of 1, is going to have the following form. And this notation will be familiar from earlier chapters. Alpha is the total return of an investor to an investor in the stock. Delta is the continuous dividend return. So if you just look at alpha minus delta, we'll see in a moment, that's the continuous price return to the investor. And then we have what may appear to be a mysterious adjustment of minus a half sigma squared. And we saw, in fact, this adjustment in, I believe it was chapter 11, where different binomial lattice models were introduced. And we'll see that in just a minute. But you may recall that the author originally introduced a binomial lattice model with a certain calibration, and then showed a couple of others. One was called the Cox-Ross-Rubinstein model. One was called the log-normal model. It was the log-normal version of the binomial lattice model, which had this form. We saw it wasn't an R, it wasn't an alpha, it was an R, because we were dealing with option pricing. It was an R minus delta, and we also saw that mysterious half sigma squared. The mysterious half sigma squared comes out of the study of geometric Brownian motion and Ito's lemma, which we're going to be seeing in a subsequent chapter. Here, let's just say we'll accept that it appears to be a mysterious adjustment to the mean. And the annualized standard deviation will just be sigma. And I make a note here that don't be confused by the calibration of these models. It's typical that if we're dealing with real-world models of stock prices, we'll use alpha, where alpha is our estimated total continuous return or continuous total return to the stock. When we're dealing with option pricing, we don't want to use R. We want to assume that the continuous total return to investors is R, the risk-free rate, not alpha. So in various models, whether they're binomial lattice or these log-normal models, you'll see this switch. It's common to use alpha when you're working with a model in the real world with real-world prices, and you switch alpha to R when you're trying to build a model with which you can price options.